Thanks. Yes. So yeah. So we'll continue the discussion I started last time on Bayesian inference, and just very quick reminder, very quickly go over what I presented at the end of my last lecture. So to recap, there's a vast array of jet measurements. If you've taken away anything from this lecture, this set of lectures, it should be that jets are very rich in phenomenology. The great challenge is to bring that richness under control, to try to use it as a tool to understand the nature of the quark-gluon plasma. It kind of goes both ways. What is the influence of the plasma on the jet? We talk about, jet phenomenology, jet energy loss, jet broadening, jet azimuthal deflections, jets inducing wakes in the plasma. But that's a little funny if you think about it. We're talking about the effect of the plasma on the jet. But we really want to answer the opposite question. How do we use jets to actually understand the plasma? And so, for instance, extracting the transport coefficient Q hat, or understanding the wake effect that I discussed, during my last lecture. So there are many measurements, the vast majority of which I haven't even touched on here. Perhaps Siddharth will talk about some I haven't talked about in this little flow diagram. And the broad question I want to address here is connecting the rich experimental phenomenology with theoretical modeling to learn about the structural dynamics of the quark-gluon plasma. And the tool of choice, I won't go in detail again, is Bayes' theorem and Bayesian inference. Is very simple in its origin. So we start off with with our prior knowledge. What do we know before we even start the problem? And we have a confined set of expectations. We want to know, in that universe of expectations, which ones are really preferred by experiment. So in order to do that, we calculate the likelihood, which is the probability given so we start off with a model formulation. That's the beginning. And it has a set of n parameters, n 3, 5, 10, 20, some number. And then for a given instance of this vector of model parameters, what's the probability that it describes the data? And we talk about probability, there has to be some uncertainty associated with it. Is it consistent? Is it not consistent? And this has to be quantifiable. So the issue of uncertainties is intrinsic in this likelihood. And then this product then gives us which parameters are actually favored by the data, given the data, which set of parameters are preferred. And the inference is to walk through the n-dimensional model space and map out the likelihood and see which sets of posteriors are most likely. That's the exercise. And it's computationally very expensive because the parameter space can be significant in calculating the likelihood at each vector, at each instance of the choice of parameters. We have to calculate jets propagating through a plasma, hydrodynamic expansion. We have to do that with statistical precision, generate tens of thousands, hundreds of thousands of events at each choice of theta vector. We have to span this n-dimensional space. You can imagine the problem is exploding computationally. Very heavy computational problem if we want to do it in this rigorous fashion. You can imagine shortcuts, but if we really want to do it, and for years, of course, people have doing it, in shortcut, we really want to do it right. It's computationally extremely heavy, and as I'll get to, machine learning plays an essential role in making it computationally tractable. We use the biggest computers, so-called high-performance computation. We use the biggest computers available to us in the US and England. We have equivalent computers here in India, and one of the things I'm discussing with my Indian colleagues is maybe, we can get an Indian effort in this Bayesian inference, exercise going. Perhaps that's something that can come out of this meeting. And there are very interesting machine learning problems associated with this. That's a little bit of advertisement for this kind of analysis. So let me go on. Right. So I'm working in the Jetscape collaboration, a collection of about 60 people. I'm not sure it's complete. We have experimentalists, theorists, data scientists, and computer scientists to all build this machinery and make it go. And there are two large components. I'm just recapping what I told you last time. There's this very elaborate physics model of hydrodynamics and jet propagation. I'll say more about that. And then there's the Bayesian inference framework. And these are both computationally large, sort of large sets of codes Takes about 10 years to build both of these, and now we're utilizing them. So I'm not going to spend time on, let me just briefly, so this was the first paper I went through last time, determining the jet transport coefficient Q hat. We all know what Q hat is now, from inclusive hadron suppression, just the simplest measurement. And that's what I discussed last time. And here's where we ended up. So now let me go forward. And now we're going to do something more. And this slide is from lecture 2. If you remember, at a certain point, I was talking about, hadron suppression. Now we add jet reconstruction. I spent some time talking about jet reconstruction and so on. Let's measure jets in the plasma and see what kind of energy loss distributions we get, inclusive jet RAA. And there was this plot that we spent some time on. Sorry, my label stepped on it, but you remember it. And I promised, let's table this question. So we have energy loss measured by hadrons, and we have energy loss measured by jets, and they're on the same plot here, and they're a little bit different. They're different physical objects, and the question is, well, there's one energy loss process. We're measuring it in 2 different ways. What do we learn? What benefit do we get from doing this very complicated, really technically, really involved exercise of trying to get the jet measurements and jet suppression distributions from the data? What additional benefit, if any, does it bring? Are we learning new information? Or are we just repeating what we already did, and there's really nothing new to be learned from jet physics? That, as opposed to just looking at single hadrons, which are much simpler, I hope you understood, are much simpler to measure experimentally. What's really the benefit of doing these kinds of jet measurements? So I said, let's table that question, and now we're coming back to it. Okay, so here is the second Jetscape paper that I want to talk about, from published last year, Bayesian inference analysis of jet quenching using inclusive jet and hadron suppression measures. And now we're walking this big flowchart I had, where now we're adding 2 boxes. And you can imagine there's a whole program here. We start adding more and more boxes. We add this ecoplanarity I talked about. Maybe we add gamma jet. Maybe we add all sorts of stuff, step by step. This is the first non-trivial step into a multi-messenger program to try to understand jet quenching. We're trying to measure the same thing in 2 systematically very different ways, see whether we get consistency. If we don't get consistency, something's wrong with our physics picture. That's great. We need a tool to do that, and this is the tool. Okay, so let's check ourselves, and this is how we're going to learn. We made this vast array of measurements. Now let's try to put it to use and figure out what we've understood. So a few words from the abstract. I like to do this rather than kind of summarize. It gives you the information directly. It's a new determination of the jet transport parameter Q hat. We've been through what Q hat is, using all available inclusive hadron and jet yield suppression data at RIC and the LHC. This multi-observable analysis extends a previously published Jetscape Bayesian inference, which I talked about last time and just showed a moment ago, which was based solely on a selection of inclusive hadron suppression data. So we're now adding jets. Data included in this analysis span a broad range in collision energy and centrality and transverse momentum. Huge kinematic range. What do we learn from that? And several different so-called calibrations. That's a term of art. When you do a Bayesian inference, the result is called a calibration. It comes from probably some engineering term. A little weird for physicists, but that's a term, and that's a term I'm going to use when you do a Bayesian inference. That's kind of what data scientists like to call the results of a Bayesian inference analysis, and that's what I'll call based on combined jet and hadron data, or we separately analyze jet and hadron data individually using the same theoretical framework and ask, do we find consistency? And we look at high PT, low PT, different kinematic ranges. This is the kind of thing you can do and say, is there one unified, consistent picture that describes all the data, or do we find tension? Is there a problem? Tension is observed, no secret. So we actually find issues with our theoretical framework. That's great. That's how we learn. We want to propose a model and then see where it breaks based upon confrontation with the data, fix it. Do it again. That's the way science works. You want to ask the right question. If you get a negative answer, your model's not good enough. Perfect. That's really how we learn. If everything works great, you don't know where to go. Okay, so a few words on the model, and Soren Schlichting hopefully and other people spent more time on this last, last week, okay, let me just forget the animation here. So the Jetscapes framework has the physics model has two major components. One is hydrodynamics and the other is the jet quenching. So we have a really detailed, sophisticated model of the hydrodynamics of the collision. And then we have one of the several advanced formulations of jets propagating in the plasma. So we model a plasma and then we create jets and send them through interacting, as we've been discussing over the last few lectures. And the parameter that controls the interaction of the jets with the plasma. So the hydrodynamics just sort of sets the environment, sets the color charge density, it sets the temperature profile, it sets the time development. It's a very dynamic thing, sets the time development. So it's a very dynamic thing. Then we put a jet in there, we let it propagate along with the development, and then at each step, we're locally examining the environment. What's the temperature here? What's the density here? How is the data flowing? How does that interact with our jet? So it's a very detailed microscopic model, and we do it again and again and again for a particular formulation of Q hat. And last time I showed one formulation of Q hat. This is a little different, and this is so we have a model for Q hat, and it's so-called hard thermal loop. That's one of the theoretical approximations that one uses. We happen to choose it here. This can be replaced by other approaches, BTM, BDM, PSZ, higher twist. There are various formulations of Q hat you could imagine putting in. This is what we happen to do for this exercise. And that's one of the interesting things with Bayesian inference, is to replace a given theoretical formulation based on a certain approximation with another and compare. What do you learn? So we do it just with this formulation. I'm not going to go through it in any detail, but I did at the beginning mention, jet production is complex because the quark coming out, we've got some hard process here, the quark coming out is highly virtual. And the whole nature of the gluon shower is the virtual quark is shaking off virtuality, and eventually the jet comes on shell in colorless massive particles. So how do you deal with the virtuality and its interaction with the plasma? It's a very interesting theoretical question. Yeah. Sorry, this is, it's a little confusing. This is the master equation, and F, this value F, this is the expression of F.
Yes, but the question is the plot which you showed. There is a Q hat with dash line horizontal, and then the one with FQ squared, which goes down as a function of Q squared.
These dash lines are, if there is no, so this is for two different jet energies, 10 GeV and 500 GeV.
Yes, that's a difference.
And this is with, so this factor F is a theoretical formulation that accounts for the change in interaction with the medium with jet virtuality. As the jet evolves, the virtuality declines. Okay, and this is the function. So if we account for virtuality, here's what Q hat looks like. If we ignore virtuality, here's what Q hat looks like for these two jet energies.
Okay, so the first line.
I'm sorry, I should use some color. The first line is the master equation.
No, not the first. The second line. The Q hat HTL over T cube.
So this is right. So this term is defined like so. It's got basically one parameter, so-called alpha S. And then the virtuality dependence. So it's the master Q hat is the product of an HTL Q hat and then a model for the virtuality dependence. Okay, sorry, it's a confusing slide, but it's so this is the Q hat that goes into the modeling. It's a function of jet energy and jet virtuality and local temperature. And we every step one examines, and so the Q hat is evolving as the plasma is evolving. And this is a means of accounting for the virtuality dependence of jet interactions in the plasma. It's got some functional form. And so now, so that's the physics. Now let's just do operationally what's a Bayesian inference doing. If we count up the parameters, there are 6 parameters. This alpha S in the HTL formulation, and this virtuality has has 4 parameters, these guys here, these C parameters, and then there's a so-called switching virtuality. So this is effective only above a certain virtuality. Once the virtuality gets sufficiently small, we just ignore it. That's a kind of a model built into the model. There were some kind of numerical reasons for that. And there's a kind of a formation time, a start time, before which there's no interaction, just a sort of a plasma formation time. So 6 parameters for the inference. Bayesian, just one moment. Bayesian inference doesn't know any physics, it just knows parameters. So that's why it's important to count. Yes. Microphone.
Are these parameters related to the AB parameters that you had used in the first paper?
No,
Is there
you can just set that aside for the purpose. Consider this there's some conceptual, this functionally doesn't look the same, right? So basically my theory colleagues rethought how to formulate Q hat. Just consider this a different model of Q hat. Now, ultimately, the physics underlying Q hat should be the same. It's just a different theoretical formulation. There are several such, and I'm not the person to talk about it. Soren last week, hopefully he said a little bit. But for the purpose of this exercise, just take this as it is. All right, good. So it's a physically motivated model. It's not the only one, and it provides us a valuable test bench. So one step after another. And it's modular. Other models can be implemented, and that's absolutely crucial for future directions. And in fact, one of the things we're working on very actively is to replace the model of the plasma and in particular the model of the plasma jet interactions with one based on ADS-CFT, this kind of string theory formulation within, this is a model by Krishna Rajagopal and Danny Pablos called the hybrid model, which generally describes phenomenology, but it's a very different model of jets interacting with the plasma. We're just in the midst of integrating that within Jetscape. It will be very interesting to compare the two. Yeah. Okay, so that's for the future. Right, so now we come back, yeah, another question?
So,
yeah.
when you want to include some other models, the main input goes into Q hat.
Well, it would be how one formulates Q hat. It may be how one actually formulates the plasma and its dynamics. Okay. Everything can be replaced. What's constant is the data sets. So we wanted the data sets, there's a Bayesian inference. So really two separate things. The physics model, Bayesian. So change this, keep this fixed, and then you can do a controlled A-B comparison.
But the plasma is very well known to follow hydro. Means there are multiple evidences from V2 and...
Right, so at this point, and it's quite, one has to comment, it's quite a remarkable accomplishment of the field that hydrodynamics is at this point not terribly controversial anymore. So really, I think that the real interesting variation is the jet interaction with the plasma. And that's where this ADS-CFT formulation of energy loss in the plasma will be a very interesting variant to replace this with that phenomenology. Okay, so that's the theory and now the data, and we saw these data before, hadrons and jets, and we're going to come back to this because the details of the data are crucial, and we'll see in a moment how very crucial they are. So here is a list of all the data we used, and this is now new in the field. So collider, heavy ion physics at colliders has been going on since the year 2000 when Rick turned on. It's a vast amount of data on hadron and jet suppression at this point. And for the first time in the field, we used all of it. There had to be a cutoff date for the study. It was, I think, February 2022. So we used all publications up to February 2022. And that's important. We chose to be very agnostic. If you go to Quark Matter or Hard Probes and you hear a theory talk, almost always, theorists, they're very pragmatic. They say, oh, I like the CMS data, Atlas data, not so much. I just plot against the CMS data. You can do that, but it's kind of, you're missing information. And more times than I'm happy to report, I ask people, why didn't you use the totality of the data? They say, well, data aren't quite consistent, so I'm going to use these data. That's not a very good scientific approach.
Does the Bayesian analysis explain to you the inconsistency between the data sets?
Does it? No,
Does Bayesian analysis explain to you the inconsistency between data sets?
Since we're on that point, I'm not going to find it in this table. There's a very important inconsistency between Atlas and CMS.
Yes.
In jet RAA at very high PT, above 400 GeV or so, they differ very significantly, well outside the uncertainties. So what to do about that? Well, that's Bayesian inference is not going to tell you which one is right. That's an experimental issue. So you have a choice. So you can put them both into the analysis and just say, I have inconsistent data. Let's see what we get. And then you can say, I analyze only with Atlas, I analyze only with CMS, and let's see what the outcome is, whether my result depends upon a specific choice. You can do all three of those, and that's the fair agnostic thing to do, right? What isn't okay is say they're inconsistent, forget Atlas, I'm just taking CMS. Not okay. But it happens. I'm not going to name names, but it happens. But be aware when you go to conferences. Anyway, so and since we're experimentalists from all the collaborations, and really it's really the only way to do good science. If there's an inconsistency in the data, it's up to the experiments to figure that out. It's not up to people. In this, I'm an experimentalist, and part of my life, other part of my life, I'm this kind of phenomenologist. My phenomenology role, it's not up to me to tell Atlas and CMS, that you're right and you're wrong. It's not my business. Anyway, so we use all data. We have a large number of data points, over 700. The previous paper, I had an order of magnitude fewer. Tremendous amount of data, and I want to stress that it's not just the central values. It's also the uncertainties which are crucial. And not only the uncertainties, point by point, but their covariance. How is this uncertainty related to that uncertainty? And there are, for any experimentalist who's done a measurement, that as a function of transverse momentum, there can be correlated effects. So that, if the truth is in the upper part of this error bar, it may be correlated or uncorrelated. You may prefer the upper part of this error bar as well. So one has to, that's encoded in what's called the covariance matrix. And so really to calculate the likelihood properly, you need the full covariance matrix from the data. And you can well imagine some of these data go back quite some time. That's not available here. So we had to make some assumptions about covariance and correlations, but that's all written in the paper. A little too detailed for today, yeah.
Interesting thing is that Alice has non-overlapping regions of PT for hadrons and jets.
Yeah, that's right.
But other experiments have some overlapping regions.
That's right. Right, they have overlap because it's this higher PT. And somebody was asking me about that yesterday. So why is the Alice jets so limited? In the lower, so this is an early Alice jet measurement, and we are extending this. This was a conservative measurement to kind of avoid the noise. This is my kind of intermediate strategy of just measuring at very high PT, so you're not overwhelmed by the noise of the heavy ion collisions. And this upper limit is due to the fact that Alice is what we call a slow detector. Alice is a time projection chamber, which is a beautiful tracking device, but its readout is very slow. So in run 1 and run 2, we could not take data at near the same rate as Atlas and CMS. We had to cut the luminosity by a large factor. This is known. And so we just don't have as large a data set as Atlas and CMS, and our phase-based coverage is less. So Atlas and CMS, that their sweet spot is very high energy jets. We just give that up. So the upper limit on the green points is just due to limited Alice bandwidth, which is now fixed with a continuous readout in run 3, and we'll go very much farther. So they're just technical reasons. And likewise for the tracking, the Alice tracking, cut off at this 50. So we've since gone much farther. So this is just a kind of a accident of the early, not accident, just a consequence of certain experimental limitations, early data sets, which have been since addressed, and run 3 will go much further. So, right. Okay. So, right, I've stressed the covariance. Right. So now let's get to it. So, yeah, so to repeat, we want to do this calculation over this n-dimensional parameter space, 6 parameters, and the computation is quite heavy. We have to do a hydrodynamic calculation, send the jet through and do it again and again at each point in this 6-dimensional space. And so you can only calculate at a limited number of points, so-called design points. And so it requires great care and strategy to figure out how to optimally span this 6-dimensional space. And as I've stressed, this is where machine learning is really essential. We use what's called active learning. It's a machine learning technique. So we initially have a set of design points chosen, what's called the Latin hypercube. It's just a kind of a way to in an optimal statistical fashion, initially span an n-dimensional space if you don't know anything about it. And then you iteratively learn the contours of the space. It can be complex, it can be multimodal with multiple peaks and multiple valleys, and you want to span that space in a computationally efficient way. You don't want to waste computational time on some remote part of the space that is unlikely to give you a good likelihood. So you have to learn as you go, and that's all I'm going to say about machine learning. There's a whole lecture to be given on active learning and how it's used for inference, but that gives you a sense of where machine learning can be very useful in really not just useful, but essential in making these heavy computations actually doable on existing computing facilities. And I'm talking about the largest computing facilities available to us. So it's really, machine learning is really critical. Right. So, okay, so what's the exercise? So I said we start off with a prior space, and we turn the crank on the inference, and we get a set of posterior distributions. And this is now, it's not Q hat, this is kind of the consequence of the calculation given, so each one of these lines you should think of as a choice of parameters for Q hat run through the whole modeling mechanism and making a prediction for REA for the kinematics of, just one example, this measurement from Alice at 5 TeV, charge hadron REA for these different collision centralities. So there's a set of data here. The red points are the Alice data, and then each one of these purple lines is a different choice of parameters in our 6-dimensional parameter space, and the prediction of the model for REA, and some of them are way off. You wouldn't want those. The ones that are close to the data, you would want. And this is just one of many sets of data, and if this were the only data we were looking at, well, it'd be pretty clear what we wanted to select. And the action, but we have many, many different sets of data which can be in tension given our model. I'll come back to that immediately. The result of the calibration, this is a result of the exercise. After we've done the Bayesian inference, these are the preferred posteriors, and they happen to fit the Alice data pretty well. Okay, so that's one microscopic look at the data. Here is the entire data set. Here's the entire data set, a lot of data. Over 700 points. I'm not expecting you to resolve any of this. You'd have to come right up to the screen. Even I can't read it from this distance. The point is to kind of get an overall impression. Again, this is the result of the calculation. And even from sitting in the back row here, you can see some red points and blue lines don't quite match. Right? In some cases. I mean, you can just sort of spend a moment and look through this gallery of results. This is all the data we took into account. There's Rick, there's LHC, there's Alice, Atlas, CMS, lots of stuff here. Some works, some doesn't. And that's the point, is that we took one model and we confronted it with an immense array of data, and we get some inconsistencies, we get some tensions. And this is kind of the net result. This is kind of the grand average of taking all these data together and saying, how well does this model work? So that's, so broadly, not too bad. There are some problems. I've highlighted a few. You can find others. I mean, not matching there, not matching there, not matching there. That tells us either the model is incomplete or the data are inconsistent. Not all data are correct. So now we can go on. So that's the kind of the intermediate step. Now let's see what we really learned from this. Okay. So I talked about this kind of correlation plot. These are this Q hat formulation. These are the key parameters. We skipped C1, C2, which weren't constrained well. This shows you how well kind of we converged on the solution. So this alpha S, which is the parameter for the hard thermal loop Q hat, is reasonably well constrained. Blue is Okay, right, I have to always remember, right. So blue is if we take all data, hadron and jet, and red is if we only consider the hadrons, we ignore the jets. We can do that. And so there's a difference in Q hat if you only include hadrons or if you include hadrons and jets together. This parameter, the starting parameter tau, not terribly well constrained, and this virtuality, C1, C2 aren't constrained at all, C3 very poorly constrained. So that tells us already maybe this virtuality formulation isn't really very well constrained by the data. Good, we're learning. So that's the kind of thing you can learn from these correlation plots. And then then the off diagonals here are now the covariance between each of these parameters. I don't think there's a lot to be learned. Let's ignore the off diagonals, just look at diagonals. So this is the kind of thing you get out of the analysis. And now we're gonna, so what do we learn? So just to kind of summarize what we learned from this, we want to know what Q hat is. And if you remember, at least from the BDMPS formulation, Q hat is sensitive to the biomass of the plasma and perhaps the temperature of the plasma. So it's a very interesting number to know. So what is it? It actually itself has a temperature dependence. And so here is the constraint. This is sort of the 90% distribution of the 90%, the central part of the posterior distribution. Here is the constraint on Q hat over T cubed as a function of temperature from this calibration. In the sense, we've now measured Q hat from the data, it has some values. And this is for all the data together. Okay, that's what it is. Now, let's do the same exercise considering only jets or only hadrons. Remember, I started off by saying, what have we learned by doing these additional measurements with jets? Is there a difference measuring jet RAA and hadron RAA? And while the uncertainty bands overlap, the central values are really substantially different. I mean, it's not, it's not, in a rigorous sense, these are consistent, but there's sufficient difference so we can start asking, why are these central values so very different? We've taken a lot of data from hadrons and from jets, and somehow the totality of the message is we get a lower Q hat, a smaller coupling to the medium of jets propagating through the plasma if we measure quenching using only jet signatures than if we measure quenching using only hadron signatures. That's interesting. We're learning what our messengers are actually telling us about the plasma. So let's come back to the data, and now I want you to pay attention to the error bars. Okay, let's really look with detail in this. So the jet data are out here. They have relatively small error bars out here, but the hadron data are really the most precise down here. And I told you the likelihood depends upon the uncertainties. Likelihood knows no physics. So it's going to be driven by the data with the smallest uncertainties. It's a black, it's not smart in physics. It just, you ask it a question, it gives you an answer. If you give it a set of data, some of which is extremely precise and some of which is very imprecise, it's going to ignore the imprecise data because it's not very constraining. That's the nature of a numerical analysis. You have to be extremely careful how you ask the question. Okay. So now let's just take a slice here at 200 MeV temperature and just project it onto this axis. And this is now the kind of the distribution, kind of the projected distribution of the posterior. So the projection of the posterior distribution sort of in this slice at 200 MeV. If we take the combined solution of all jet and hadron data together, we get the purple curve. If we only consider hadrons, we get the orange curve. If we only consider jets, we get the blue curve. And this now looks fairly incompatible. And if we now look in detail at how well the fits go, if we only consider hadrons above 30 GeV, we get substantially better fit than if we do the entire data set. So now, let me see if this is, yeah, this is live, good. So now what we're doing is we're looking at the posterior distributions and we're setting thresholds on the PT of the hadrons we're considering. So the jet solution is in blue. The total hadron solution is in orange. And if we only consider very high PT hadrons, the gray here, it's very much compatible with the jet solution. In other words, low PT hadrons are giving us a different answer than jets and high PT hadrons. There's some kind of different physics going on as a function of PT of the hadrons in terms of understanding how well jets are interacting with the plasma. So this sounds a little technical, but it's really crucial in understanding how well our model is working and how well we're understanding the interaction and how that of the jets with the plasma and how that manifests in our final in our understanding of quenching. So somehow there's something missing in the model. The PT dependence of the model does not describe the data well. There's somehow an inconsistency. So why am I concerned about the inconsistency? Q hat should be a property of the plasma. It should not depend upon the probe we're using. We should get a fully consistent picture if Q hat were only a property of the plasma. We probe it two different ways, we should get the same answer. We're finding inconsistency by probing it in two different ways. That kind of turns the circle, it closes the circle to my initial motivation. We want to do multi-messenger physics and get the same answer. We are not getting the same answers. There's something wrong with our theoretical formulation. Yeah, question up there.
So here you have considered jet, there is no constraint on the PT of hadron or PT of the jet, right?
Well, here we are varying the hadron PT
Hadron
being
PT, but
taken into consideration.
jet PT you considered entire PT range available
yes.
for the experiment?
All the measurements.
All measurements.
Yes.
So means you are going very high PT.
That's right, but then the error bars blow up.
And then
It turns out, so we did that exercise and we go back to the data, right? So it turns out that these data aren't, it looks small here, but the CMS data have a rather large uncertainties. These data are not terribly constraining, it turns out.
So my question, is it possible, for instance, in the PT range where we have both hadron and jet array available, using only those data sets, can we check how they compare?
Well, that's more or less this. That you would just consider the gray guy here. Sorry, it's dynamic here. Just consider the gray guy. That's more or less.
More or less, hadron is.
Yeah, if we only look at very energetic hadrons overlapping the PT range of the jets, we get the same answer. So as a function of PT, somehow the dynamics are changing in a way that's not captured in our model.
Okay.
That's the lesson. So yeah, so that's really the outcome of this exercise. And the reason I spent so much time on it is we need a tool to allow us in an agnostic fashion to compare data and theory and to tell us where there are problems. And here it is. So now, my theory friends can go back and think, well, maybe my formulation, the HDL formulation of the virtuality wasn't quite right. What's going wrong with the model for low PT hadrons? Why am I getting an inconsistent, solution here? Maybe there are other issues in the calculation to do with PDFs and so on. We now have to start thinking what can actually fix this problem. So my message of this lecture is really not, the physics per se. Clearly there's some issue and I don't know how to fix it. It's really the instrument, the tool to reveal the problem, which will allow us then to make the next step in addressing the physics. Okay? Well, that's what Bayesian inference can bring. All right. So so let me stop here with the Bayesian inference. So okay, sorry, but just what are the next steps? Well, certainly, the model formulation needs to be addressed. Probably the virtuality dependence needs some rethinking, and we can also expand our universe of observables, bringing in jet substructure, bringing in coincidence channels like photon jet or the hadron jet that I talked about. Heavy flavor, which I mentioned yesterday, is also exceedingly interesting to bring in. This would require a new kind of module for modeling the interaction of heavy flavor with the medium. Rainer Fries, who you know well, is the guy who's in Jetscape, and this would be a very interesting addition, I think, to this whole framework. We have to do it slowly and cautiously. Clearly, there's a lot of computation that you need to use very carefully. New models, I already indicated bringing in the hybrid model will also be of great interest. So, okay, so let me stop there with the Bayesian inference and then take questions and then I can go on to my next lecture. Any questions on Bayesian inference before I go on? Nope. Okay. So where's Nihar? Can we go to lecture 4? Now, from a perturbative point of view, modeling, the calculation of low PT hadrons is least certain. There's a lot of non-perturbative effects that can come in. And what we are missing in this calculation is theory uncertainties. So one way to fix it is to add realistic theory uncertainties and how well we're actually able to calculate the rates of production of low PT hadrons versus high PT hadrons, where the theory uncertainties should be smaller. They go opposite to the way the experimental uncertainties go. These are not accounted for. We have no way of accounting for them right now. So that's an essential missing element in the whole picture. Okay, more questions before I go on? Yeah.
Your model for Q hat, your model for Q hat, you took alpha as a parameter for a fixed temperature and also
Sorry,
running. In the model for Q hat, you took alpha as a running coupling and also as a model parameter at fixed temperature. So what was the reason?
Why is the coupling running?
Yes.
It's a bit suggestive to use the phrase alpha S. There is no, alpha S is a fundamental constant, but it's Q squared dependent. And these processes are integrating, let's call it an effective coupling. And it will run with, with Q squared. So it's, maybe the best way to say it, it's just an effective coupling sort of approximates the role of alpha S in interactions in this hard thermal loop formulation. Yeah.
Yesterday, you showed a plot at which you put a cutoff where you start to define jet versus hadrons, right, at 5 GeV. The data that you showed before here today, small PT means what, 5, 10, or?
Right, so in fact, there's a little detail. So we ignored hadrons below 10. So,
so you ignore all
so we
final
didn't
state
take
rescattering or
take literally all data. We ignored hadrons below 10 GeV.
Below 10 GeV. Yeah. So there is no issue of rescattering in the hadronic.
Yeah, there are many things. In principle, we could include it. And
that would be an obvious discrepancy in the theoretical modeling of Q hat, of course, yes.
Yeah. Okay. Let me just get a drink and then we can continue with the next. Right. So now my last lecture, and this is sort of less pedagogical and more in the sense of a seminar. And where I'm going to wind up is not results so much as a proposal for how to understand gluon saturation in a comprehensive way. So, but if I'm going too fast and technical, of course, ask questions and slow down. So, okay, so let's recap something, a few slides that I showed in lecture 1, some basics of QCD. So if we consider deep inelastic scattering of a proton and an electron comes in, knocks out a quark, and we have complete kinematics, and we can really measure the structure of a proton in this way. We looked at this quantity F2, which is sensitive to the structure of a proton, is measurable and is calculable. And we found that it has, first of all, beautiful data and really indicates that Q squared, the momentum transfer is which resolves different length scales within the proton is absolutely crucial to understand proton structure. Proton structure is strongly dependent upon Q square. Partonic densities are not point-like, and the hadron structure depends crucially on the scale at which you probe it. Furthermore, there was spectacular agreement with what I call linear evolution in Q squared, such that you start with some distribution at at some value of Q squared, and then you evolve the densities. So you evolve the gluon densities, not taking into account of the environment, the fact that there are other gluons around. So we'll come back to what linear and nonlinear means in a moment. And this is a tour de force of perturbative QCD, and really led us to a deep understanding of proton structure in terms of parton distribution functions as a function of Q squared. At small Q squared, large transverse length scales, the proton looks simple, primarily valence quarks. As you go to large Q squared, very fine transverse distances, it becomes extremely complex. The gluon densities grow very rapidly. So that was all from lecture 1. And let's focus now on this very rapid growth of the gluon densities towards low x. So we get lower and lower in x, smaller and smaller momentum fraction. The gluon densities seem to be exploding. Can that go on forever? No, it cannot. Because QCD is non-abelian, gluons carry color charge, they interact between themselves, and they have all these complex interaction structures. And as the gluon density grows and grows and grows, it eventually has to be self-limiting. You get sufficiently high densities, the gluons will recombine because they interact between themselves. So eventually, just completely generically from the fact that QCD is non-abelian, gluons carry color charge, at sufficiently low densities, sufficiently low x, sufficiently high densities, gluon saturation must occur. It's almost trivial given the nature of QCD. But that doesn't tell you much. Doesn't tell you where, doesn't tell you how, doesn't tell you what this state of saturation really is. And there's been a lot of work over the years. I mean, this was realized not long ago. A lot of the work over the years to really understand the nature of gluon saturation. And in particular, there's a very interesting effective field theory formulation called the color glass condensate of this low X regime. It incorporates the nonlinear evolution of low X gluon distributions. As you go lower and lower, gluons recombine, they create essentially well, it's in the name, color glass condensate that has very special dynamics. So that's an interesting regime of QCD, and it's been discussed for a long time. How does it affect, for instance, collisions at the LHC? Well, that's an interesting question, but I think it's also, certainly is also an interesting object in its own right to investigate. It's the focus, for instance, of the electron-ion collider that's under construction in the US. So this is the way we like to express the hadronic structure phase diagram at high X and high Q squared. The proton or any generic hadron is fairly simple. And as we move in this diagram at fixed X in Q squared, we have linear evolution in so-called DGLAP, I've already mentioned. If we fix Q squared and we evolve in X in this low density region, it's likewise a linear evolution, so-called BFKL equation. But now we get down in this corner of very low X and low Q squared. We're looking at large transverse length scales and very low momentum fraction where the gluon densities are very high. What's going on here? And eventually this linear evolution needs to transform into nonlinear evolution. And there are two equations that govern this evolution. The simpler BK, Bielitsky-Kovchikov, and then the Jimwalk is the complete solution. And eventually the evolution needs to go nonlinear and we get into this saturation regime. Now you notice there are no numbers on the axes because nobody knows where this is. Nobody knows where this occurs. And that's really the question. So we have linear evolution, nonlinear evolution. And we can ask, is this the correct description of the low X structure of matter? And an experimentalist, I ask, how can we explore it experimentally? And that's really my subject today. So let's go back to this beautiful plot of the X and Q squared dependence of F2 as measured in at Hera, and the absolutely spectacular agreement of DGLAP linear evolution with the data. And let's look at it a little carefully. So a lot of precise data. This is only a limited subset of the total data. They plot it this way for clarity, and this is good enough for our purposes. And let's think, what if the world were different? What if we didn't have all the data, but we only had, say, a few data points here? We wouldn't know much. You wouldn't know how well DGLAP agreed. You wouldn't be able to say much about, the evolution, the nature of evolution. Is linear evolution really describing the data? Any single data point or a few data points say rather little. What's convincing, what's deeply convincing about this plot, which convinces us that QCD is really working with extraordinary precision, is actually the totality of the data over a vast phase space. It is the high level of agreement of theory and data over a vast kinematic range that is convincing. That's an interesting fact. If we think about how to explore saturation, well, the same has to be true. We talk about gluon saturation. What we're really talking about, we don't just want to measure one observable in one point down here. It wouldn't tell us much if we measure direct photons at an x of 10 to the minus 5 and we see a suppressed rate. What do we do with that? Not much. The convincing case for saturation and is to measure evolution. In other words, measure observables sensitive to saturation over a vast kinematic range, just like was done here. In order to discover saturation, we have to redo this exercise, but now push to very low x, low q squared. So that means, QCD phenomena generically evolve logarithmically in x and q squared. That's kind of the way QCD works. And so we need very broad coverage in x and q squared, not just one limited range for one experiment. And then there's this concept of QCD universality. QCD is the gauge theory of the strong interaction. It's not the gauge theory of the strong interaction only as measured in deep inelastic scattering or only as measured at the LHC. It's a theory of the strong interaction. So if we have a correct description of physics in the saturation regime, we have to be able to measure it using meaningfully different probes and get the same answer. So-called universality. The correct theoretical description at low x must self-consistently describe measurements of multiple observables at low x in multiple collision systems. So this is really expanding the scope of low x physics beyond just looking at the EIC or just looking forward at RIC. In fact, we have to bring them all together in a comprehensive program. And this is a term I like, and I use it again and again. Low x physics is likewise a multi-messenger program, combined measurements from EA and EP in deep inelastic scattering and diffractive interactions at HERA and EIC with forward PA collisions at RIC and the LHC. Not just EIC, not just HERA, but all four of these together in a meaningful way that's theoretically well controlled. Very ambitious program. And it won't surprise you that the framework to do that, and this is a connection to the previous talk, and the reason I'm adding this here, is the right way to do that is using the framework of Bayesian inference, which is an agnostic tool to bring together complex data, complex heterogeneous data, and complex calculations, and confront them in a consistent, rigorous fashion. So what we're going to do, and what this talk is about, is to examine both the experimental and theoretical possibilities to bring together these very different colliders, very different sets of data, and see whether a Bayesian inference program actually makes sense. And it has to be really rigorously well controlled from both the theory side and the experimental side. So first from the experimental side, whoops, that got rotated. I wonder why that is. Okay, so you're gonna have to turn your head. So the figure is right, but it's sort of, okay. So this is the kinematic coverage of the Large Hadron Collider in run 2, and most importantly in run 4. This circle should be here. This is the coverage of the LHC experiments in rapidity space. So you want to go, if you want to go to very low x at the LHC, you have to go very forward in rapidity. So what's of great importance is high rapidity. LHCb is a beautiful device at forward in one with, it's a one-arm spectrometer at forward rapidity. So you're going to turn your head. Look at, this is the rapidity axis. At forward rapidity, ATLAS and CMS have very broad coverage, and they're extending it somewhat in run 4. Look at the hashed, look at the hash guys here. There's some upgrades going on, and very significantly, I'll talk about this now for a second, is an upgrade to ALICE, which is extremely forward, called the FOCAL, and there's an important Indian contribution to this upgrade. So sorry for the rotation, but let me talk about the FOCAL for just a second. So ALICE, this is kind of a cartoon of the ALICE detector. It's got a muon arm on one side and is currently open on the other, so there's an opportunity. And some years ago, some of us realized there's an opportunity to put a very forward next generation calorimeter to do extremely low X physics. So what's low X? You have a proton. Imagine running LHC with lead and proton, and you want to look and kind of backscatter off the lead nucleus. You want to look at the proton going very forward direction, and that will probe extremely low X in the nucleus. Everybody with me? So we want a very forward detector on this side of ALICE, and it turns out it's open. And the so-called FOCAL, forward calorimeter, which is a next generation high granularity silicon tungsten sampling calorimeter, extremely fine granularity. Yeah. Sorry?
Is it the same 0-degree calorimeter?
Same as?
0-degree calorimeter?
No, it's completely new calorimeter. Completely new calorimeter. And the key is silicon tungsten sampling with very fine pixels. And the idea is to be able to measure direct photons at rapidities 5 and above. So in order to do that, you need to distinguish one photon shower from 2 from the pi zeros. And so there's extremely fine pixelization. Same as?
0-degree.
No, there's a rapidity coverage 3.4 to 5.8. 0-degree calorimeter is literally 0 degrees. So this is extremely forward. And the flagship measurement is isolated direct photons above PT above PT of 2 GeV at rapidities of 5 and above. So, and I'll show the actual acceptance in a moment. So that's a flagship measurement. It can do many other things, pi zeros, jets, UPCs, Zs, Ws, et cetera. It's being installed during LHC long shutdown 3, which is about to start, and will be implemented for LHC run 4. And so now here is the coverage in terms of X and Q, and FOCAL is in red, and it goes down to a few times 10 to the minus 6 at Q of 2 GeV. So extremely low X coverage. This is for proton nucleus. For proton-proton at 14 TeV, we get down into the 10 to the minus 7 range. It's extremely low X. EIC is here in yellow. EIC is a very nice device, but because of its much lower energy, it covers it doesn't begin to approach the kinematic reach of the FOCAL, and that's the point. The FOCAL adds very interesting channel direct photons at extremely low X, and is an essential element of this low X program. So this is for electromagnetic observables, photons, Drell-Yan, and so on, and this is for hadronic and UPC observables. The LHCb measures also very low X. Very low Q. These are LHCb D mesons. Very forward charm is likewise extremely interesting. So LHCb and FOCAL, ALICE FOCAL, I think, are the key devices in run 4 to really undertake this low X program. So that's the experimental landscape. Now let's look at the theoretical landscape. We can make beautiful forward measurements at the LHC, but if they are not rigorously well described theoretically, you haven't done much. So one has to apply the highest standards for both the theory and the experiment if you really want to carry out this program in a convincing way. So it turns out that indeed there is a rigorous theoretical framework for understanding not just deep inelastic scattering at low X, that shouldn't surprise you, but also very forward hadronic collision measurements for inclusive pi zeros, jets, direct photons, and others, using this well-established dipole formalism. And furthermore, years of work, lots of theory effort has gone into establishing that multiple processes in DIS and forward PA are described theoretically by a formalism that incorporates the same forward scattering amplitude at T here. And these are calculable at higher order. So that's a very interesting opportunity. There are certain channels in forward PA that share the same theoretical description as DIS. So this is really what we're looking for. This has been a long development, even predating QCD. Here are some of the foundational papers in establishing the dipole formalism for both DIS and forward hadronic interactions. So from the theory standpoint, things seem to be quite solid. And here's actually a nice, let me just put these together. Here's a nice text from a paper that was written some time ago for the EIC, so-called Yellow Report, which kind of puts this all together. It says PA collisions can serve as a gateway to the EIC as far as saturation physics is concerned, playing an important and complementary role. There are two fundamental gluon distributions, the dipole and the quadrupole. Small x factorization in DIS and PA are expected to hold at higher order. So there is likewise a rigorous theoretical formulation for describing both DIS and PA. And here's a nice table done by my LBL colleague, Feng Yuan and others some years ago, which sort of maps out a few typical measurements in DIS and PA, and which one of these, dipole or quadrupole gluon distributions it's sensitive to, has a little bit of a scorecard here. And if you're interested in the dipole distribution, there's some measurements, gamma jet and PA, inclusive DIS. You can imagine now a scientific program that walks through DIS and PA measurements and then asks for consistency across this set of measurements. That's a strategy. So there's an opportunity here, and let's see how we can take advantage of it. So now I want to turn to kind of formulating this within a Bayesian framework. And to recap from my previous lecture, you start with a physical model, which has some parameters, and then you want to explore that parameter space by confronting with data. So what's the physical model for exploring low X? And here there's a nice paper that came out last year, which I think is an interesting worked example. It only confronts Hera data and only does a simple chi-squared. But the formulation, I think, is very suggestive of where we need to go to generalize this to a full Bayesian inference framework. So this paper is by Christoph Kutak, Anastasto, and collaborators. These are known kind of in the low X field. Revisiting gluon density from the BK equation. This is the nonlinear evolution equation for the dipole with kinematic constraints in large X term. So this paper analyzes small x nonlinear evolution, supplement as well with some corrections. And the solution to the equation is then used to perform a fit to deep and elastic scattering, reduced cross-section data from Hera. So simple exercise with nonlinear evolution, but I think very illustrative of where we need to go with the Bayesian inference. So I'm going to go through it in a little detail. So here is the actual BK equation. I don't expect you to read it in detail, but let me walk through its main features. You conjecture a starting distribution at high X, and then there's a linear evolution part, and then there's a nonlinear evolution part. The F is the gluon density, and you can see there are some terms that are nonlinear in F and some terms that are linear in F. So this is a nonlinear evolution in the gluon density. You start at high X with some conjectured starting distribution, and in this case, there's this. This is a kind of an old ansatz for the starting distribution that dates from many years ago. Golek, Biernat, and Wusthof were looking at Hera data, trying to see is there any evidence for nonlinear evolution for saturation in Hera data, and this is their formulation. Let's just take it as a formula for now, and it has a bunch of parameters. Sound familiar? There's a bunch of parameters in the initial starting distribution at high X. And then we want to evolve down to low X and see how well it matches the data. Okay. Yeah.
Nonlinear evolution has an alpha S times log, which is a well-known thing.
Sorry?
The nonlinear evolution part has an alpha S times a log, which like RG improved perturbation theory must have.
Yes.
But the linear evolution equation, that logarithm is not there. So,
Yes.
why it is so like because alpha is all the skill, running skill is absorbed by the alpha is bar there.
Yeah. So you're asking why
Why I would expect a log also in the first term. So if it's not if it's missing there, where that's absorbed.
maybe Jean-Paul has a comment. I'm not able to answer that question.
Depends on two scales, K and K prime, and I forgot, I must admit.
Yes.
Yeah, I
It's
mean,
not the way I would have written this equation, but okay.
I mean, with my naive understanding, alpha should depend on only one scale. But the linear evolution term is appearing with two scales, so it's a bit confusing.
Okay.
Yeah. Okay.
I'll take that as a comment.
Yeah.
This is not my expertise. So
Yeah.
Jean-Paul has a comment, otherwise maybe we need to go on. Yeah. The microphone.
Because I don't know this paper, and but I guess for the discussion you're having, I mean, the general structure is good enough.
Yeah. So sorry to be so casual about it. My interest is in the general structure. The details are of course important, but my interest is in the general structure. Right. So the initial starting distribution has a set of parameters, and this is what we want to constrain based by confronting the data, and we're going to compare it to what's called reduced cross-section data. Essentially, the F2 with some adjustment. Essentially, the data I showed previously for the comparison to DGLAB. So here is the solution with a set of parameters whose numbers we don't care about. What we do care about is how well this exercise reproduces these reduced cross-section data. So this is, again, some ansatz for the high X gluon distribution, now evolving to low X and comparing to this vast set of data. It's not Bayesian inference. This is just a direct calculation and then a chi-squared fit. It works extremely well. You can stare at it. You won't find any significant differences. Now, excellent fit over a vast kinematic range. Now there's something kind of funny here. I previously showed agreement to essentially the same data, agreement of linear evolution, equivalently good agreement to the same data of nonlinear evolution. Hera data cannot discriminate linear from nonlinear. We have two different theory formulations, both of which work fine. That means the nonlinear evolution has no strong influence in the kinematic range covered by Hera. We have to go farther. We need new data. So this is already a physics conclusion one can draw from this exercise and tells us we need to go a little farther. Yes.
Question. I mean, I can't read here. What is the lowest value of Q squared here? It's 2 GeV squared?
Yeah, 2 GeV squared. Yeah.
And in the plot?
And this goes up to
in the other plot.
Sorry?
In the other plot, what is the
6. That's 6. That's 2.
Okay, so
this is to repeat, this is only a subset. There's only a subset. Well, 6, yeah, okay, fine. But just to defend. So this is, for clarity, they only plotted, it's the same data. And there are plots. I actually was looking, I couldn't find one that's as clear as this one. The data go down to 2 GeV squared also for this exercise, and you would get the same message. This is only showing a subset of all data. This is the entirety of the data. So I think this statement holds. It's not that the data selections are different. Okay. But you're right. I mean, the low Q squared is crucial. Yeah, but then the question is how much? Well, this nonlinear, right? So good. I think I get your point. We would have to look at the 2 GeV squared here and see how well it does. All right.
It is a mystery.
Huh?
It is a mystery.
It is a mystery. Yes. Good. So that's an interesting exercise, computationally intensive because well, let me just point out that the integration, this is it's a multidimensional integral, and calculating this is computationally intensive, and if you have to calculate it again and again for different choices of parameters, this becomes computationally heavy. So again, in this low X exploration game, computational efficiency likewise becomes crucial if you want to do Bayesian inference and explore this parameter set in a rigorous way. So, right, and the fit is a simple chi-squared degree of freedom, not a Bayesian inference fit. So let's now come back to Bayesian inference. We've been through this. So this is Bayes' theorem. You sample an n-dimensional likelihood. So you have a parameter space of n dimensions, and you sample the likelihood with sufficient granularity, and the posterior is the prior constrained by the likelihood. Computationally demanding, the integration of this pk, and even more so the Jim-Walk equation, is computationally extremely expensive, and we have potentially a large parameter space. So one really needs machine learning to help us. So this is really the point of the talk and the proposal, and with some colleagues, I'm writing a new paper on this to really propose bringing together these heterogeneous data from RIC, LHC, HERA, EIC in a one sort of grand Bayesian framework. But how do you actually do that in practice? Because each different measurement channel requires a different theoretical calculation. And so here is a kind of a workflow or flow diagram for the simplest kind of observable one can imagine, F2 and FL in deep inelastic scattering. And so this just tells you what the calculation would have to consist of. So you would conjecture initial conditions for a dipole-gluon distribution. That's the Golek-Biernath-Wusthof. That's why I spent the time going through this. We would conjecture an initial distribution like this. Conjecture with parameters, conjecture an evolution equation, linear or nonlinear. And then, that then generates, then we turn the crank on that and we get some dipole-gluon distributions, we hit them with a virtual photon, and we calculate some cross sections. This generates simulated data, which we then compare to experimental data and generate a likelihood, and then we do the Bayesian inference exercise. So that sounds simple. Basically, the reason I went through this simple paper a moment ago is you now get a sense of the elements that go in here. So that would be 4 simple deep inelastic scattering F2 data, relatively clean data. If we want to do the same thing for inclusive hadron production, let's say forward pi zeros measured in the focal, these pieces remain the same, and that's the point. We want to use the same initial conditions and the same evolution equation. But now the calculational tools from here onwards need to change because we're measuring hadrons and not F2 in DIS. So we get a dipole-gluon distribution. Now we have to actually calculate differential cross-section and proton nucleus collisions that produce forward pi zeros. And along with hadronic collisions comes all the complication of initial state parton showering, final state parton showering, hadronization, various things we've talked about. There's no escape. If you want to measure, if you want to use forward or consider this a forward charm, d mesons from the LHCb experiment, all of these elements have to come into the calculation. You have to know how a charm fragments into a d meson if you want to use forward Ds from the LHCb experiment to constrain low X. I'm not saying it's simple, but writing down the elements means that we know one by one what we need to knock off. And when we get to the likelihood, we need to know what is the uncertainty in our hadronization parameterization that needs to go into the likelihood in order to compare the calculation with the data. So it sounds like a daunting task, and indeed it is, and it's a multi-year project, and not every measurement observable is of equal validity because of calculational limitations. Direct photons, for instance, do not have a hadronization problem. One has to worry about isolation and whether you're comparing, theoretically comparing the right calculation to the measurement. That's a different set of problems. But the point is to write these down and then debate and discuss each of these boxes, give it a try and see how close we get. This is what's needed in order to carry out this comprehensive, broad-based, large kinematic range attack on the low X physics. So we actually have a series of these workflows. Here's now what's changed is from hadron, goes to jets. And here the hadronization becomes simpler because we're integrating over hadronic degrees of freedom. So the uncertainties here would be rather lower, but now we have jet reconstruction coming in. And finally, for dijet production, this probes the quadrupole gluon distribution, and we have to do the full bore Jim-Walk evolution, and that adds an extra element here. So that's what's changed BK to Jim-Walk, but you get the sense of it. So in order to carry out a comprehensive attack on low X physics, bringing together heterogeneous data from different colliders, RIC, LHC, HERA, EIC, this is what one has to do. And that's kind of my message. So it's a very challenging program. I didn't stress here, let me just point out, machine learning comes in 2 points. Bayesian inference, I've already discussed how machine learning is important for inference, for an efficient navigation of the complex likelihood space in many parameters. Likewise, the integration of these nonlinear evolution equations, which are multidimensional, really needs to be sped up and made much more efficient using machine learning tools. You learn the integration, and then you can use your machine learning model to carry out this exploration in the parameter space very much more efficiently. Yeah. Yeah.
So, it's a wonderful diagram. I was wondering, there are even more than 2 places you can actually apply machine learning. One obvious part is the event generation, where of course you can do a lot of generative models,
yes.
right? And for the likelihood part, there are both modeling of likelihood functions using machine learning, and then there are also discussions of likelihood-free inference.
Yes.
So are you also planning to venture those directions?
You asked too much. Yes, absolutely. I mean, everything is possible. This is how far we've gotten. I mean, we spent a lot of time, these diagrams are not accidental. If you go through, F2 is an obvious one. And for most of the low X field, they don't think beyond F2. So if I can just kind of in a nutshell, what's new here? What's new here is bringing in forward hadronic, forward measurements in hadronic collisions. That's what's new here. It's a radical proposal. It's based upon this, this claim that there is rigorous formal theoretical basis for calculating. If there weren't, forget it. But now there's all this additional complication we know well, but we have to write it down and we have to address each one of them. So so there's inclusive. Let me just go through the 4 of them: inclusive F2, forward hadron production, say forward pi zeros, forward jets, and then dijets. You can think about gamma jet. I didn't put inclusive photons. These are also important. And as we work, we're going to discover that the uncertainties in some particular choice of channel, either experimental or theoretical, are so overwhelming that we have to set it aside. Some measurements are going to be more discriminating than others, and that's all part of the exercise. And as we work, yes, event generation and likelihood calculation, these will also benefit from efficiency. This is as far as we've gotten to kind of propose this framework, and now we have to think about each box and how to optimize it. So that's all. Thank you.